Hey guys, this is going to cover section 16.2. It's only 2 pages, so hopefully it's not too bad, and some of it's review. So here we go. So this section is all about the masses of atoms. In the last section we talked about a couple of these ideas, that protons and neutrons have a mass of 1 AMU each, and electrons are really itty bitty. So we're just going to kind of get into a little more detail about how that works here. In science, most mass is measured in what? So back in August, if I said find the mass of this, you would have put probably the unit grams on that, right? Or if we're talking about things that are bigger, more massive, we would maybe use kilograms. But when we're talking about atoms, they are so itty bitty tiny. So atoms are too small to make these units practical, because we would just have an astronomically small, itty-bitty, tiny number of grams, even if we're talking about a lot of atoms. Okay, so we made up a different unit. Most massive atoms we measure in atomic mass units, or AMU. Protons and neutrons each have a mass of basically 1 AMU. They're almost the same size, and for our purposes, we're just going to say they each have a mass of 1. Here's another one we kind of have already talked about here. So the atomic number is only measuring one of our 3 subatomic particles, and it is always the number of protons. Okay. If you want to know what the atomic number of an element is, it's very easy. If you have a periodic table, remember there's one of these, I believe, in either the front cover or back cover of your book, or remember there's a really nicely one at ptable.com. But here's one that I printed so I could kind of throw it up here easily. So here are some of the periodic table here, and in each box there's a couple numbers. But there's always one that's a whole number and one that has some numbers after the decimal point. When we're wanting to know how many protons, okay, I cannot have part of a proton, right? I have 1 proton or 2 protons or 3 protons. So the number of protons, or the atomic number, has got to be the whole number. And you notice it just goes up by 1 every box. So I should have 5 protons, 6 protons, 7 protons. And so it's always the whole number on an element square of the periodic table. Another way, though, that's useful to talk about atoms is their mass number, which is the sum, which, remember, in math, sum is when you add them together. So if I add together the protons and neutrons, I have the mass number. And if you're like me, your head's thinking, okay, so there's 2 numbers in the periodic table, this one must be the other one. And unfortunately, you'd be wrong. All right, so protons and neutrons each has a mass of 1. So if I'm adding up all the protons and neutrons and their mass is always 1, am I ever going to get something with a number after the decimal? Again, no. Okay, and the reason they don't put these numbers on the periodic table is this is for one individual atom. Okay, so I could have 3 atoms of carbon, and they might all have different mass numbers. Okay, they must have, if they're carbon, must have 6 protons. That's what makes them carbon. But I can have carbon with a mass of 12, carbon with a mass of 13, carbon with a mass of 14, because they can have different numbers of the other subatomic particle we're talking about here, which is neutrons. So almost all, there's a really big blank to write mass, all of the mass of an atom is protons and neutrons. So this is a simple way to compare masses of atoms. And another thing that's useful here is if you know the mass number, so you know what they add up to, and you know what element it is. Okay, so maybe I know the mass number of an atom is 13, and I know that it's carbon. So I find carbon on the periodic table. I say, oh, well, it's carbon. That means it has 6 protons. If protons and neutrons together add up to 13, and 6 of them are from carbon, I must have 7 neutrons. So we can subtract the atomic number, which remember is the number of protons, to get the number of neutrons. But really you can just kind of think about it like this and as an equation here. So the mass number is the sum of, or you add together, protons and neutrons. Okay, so we got 2 examples, and if you write nothing else out, please write out the examples so that when you have an assignment you know what you're doing. So an atom has 7 protons and 8 neutrons. So I look back up at my equation. Okay, so I'm just going to go M for mass number equals number of protons, 7, plus number of neutrons, 8. 7 and 8 is 15. And the unit we said we're going to measure mass of atoms in is AMU, atomic mass units. Alright, so that one's pretty simple. If you know protons and neutrons, just add them together. Okay, this one is kind of, you have to rearrange and think a little bit more here. It's an atom of oxygen, has a mass number of 17. How many neutrons does it have? So let's see what we know. It says mass number of 17, so that's going to go on the left. And then that's the only number we're given. We only have one number, okay? But we're told that it's oxygen. So I go to my periodic table, I find oxygen. How many protons would any atom of oxygen have to have? 8. Okay, it has to have 8 protons. So I'm going to have 8 protons plus neutrons. So my unknown, my number of neutrons is plus 8. So I'm going to subtract 8. Number of neutrons equals 17 minus 8, which is 9. I hope. No, it is. Okay. All right. We have 1 page left of this section. All right. Atoms of the same element, that means they must have the same number of protons, but with a different mass or different number of neutrons. And these are called isotopes. Okay, I'm going to grab a piece of paper here. Okay, so I'm going to just draw the nucleus here. So I might have carbon 12 and carbon 13. Okay, when we write them that way, that number is the mass number. Okay, so if I had an atom of carbon, and I want to know, well, how many protons and neutrons would be in its nucleus. So again, I find carbon, looks like it should have 6 protons. So I'm going to draw 1, 2, 3, 4, 5, 6 positive protons. Okay, so that's the 6 protons, that's what makes it carbon, but it says its mass is 12. So I need 6 more mass, basically. And so that's got to come from neutrons. 1, 2, 3, 4, 5, 6. And there would be electrons flying around too, but we're just going to kind of focus in on the nucleus here. So then we also have carbon 13. It's still carbon. Since it is still carbon, it still must have 6 protons. So I'm going to draw my 6 protons. They're all positively charged. But now my mass is 13. So how many neutrons would I need? 7. Okay, so these two would be isotopes to each other. Okay, I kind of like to think of isotopes kind of like the word cousin. It's a word for how things are similar but different. They're related in some way. Okay, so these two are similar in that they're both carbon, but different in their mass number. And that's what makes them isotopes. Okay, that they're similar, same element, but different mass. So they're defined by their element and mass number. So carbon 12, since it's carbon, this is the exact same example that we wrote out. I might as well put it back up here. Carbon 12 would have, since it's carbon, 6 protons, and since its mass is 12, also 6 neutrons. While carbon 13, since it's carbon, all carbon would have 6 protons. But if our mass is going to add up to 13, we would need 7 neutrons. All right, so isotopes of an element tend to behave the same. So I could make the same molecules with carbon-12 as I can make with carbon-13. So they behave the same in reactions, but sometimes there's an isotope that is more stable, while others we can call radioactive. Okay. And the last remaining isotope of carbon is carbon-14. So it would still have 6 protons because that's what makes it carbon. Now it would have 8 neutrons, and this one is radioactive. Okay, which means that if you had a bunch of carbon-14 and you let it just sit there, it would slowly kind of break down and its nucleus would actually change into a different, more stable element or isotope. In the case of carbon, one of these neutrons actually kicks out a negative charge to become a proton, and then it becomes nitrogen-14. So radioactive things just means the nucleus is unstable and might break down over time. So when it says go back to example 1 and 2 and write their isotope names. So here's our 2 examples here. So if this had 7 protons, so the isotope name is the element and then a dash and the mass number. So if it had 7 protons, what element must it be? It's got to be nitrogen. So you can either write out the whole name or you can just write the symbol N for nitrogen and then a dash, and then the mass number was 15. So there's the isotope name, or we can write nitrogen 15, doesn't matter. All right, so then on this one, we're told that it's oxygen. We can go O or oxygen, then a dash, and then the mass number. So the mass number on this one was 17. Okay, and those are both equally correct ways of writing the isotope name for me. All right. E says, sometimes referred to as atomic mass, and there's a really big blank here for a reason. It's a long one. Average atomic mass. Okay. So this is one that people get really, really mixed up with mass number. Okay, and here's the difference. This one, again, is for an individual atom, for one single atom. Okay, so like the mass number for this nucleus is 12. The mass number for this nucleus is 13. The mass number for this nucleus is 14. But when we're talking about average atomic mass, we don't want the mass of any individual atom. We're looking for the average of all of the atoms of that element. And so this is that decimal number off the periodic table. So this is saying if I took every single atom of carbon in the world and averaged their masses, it would be basically 12.011. Okay, so you notice about that number, it's really close to 12. Okay, which means 12 is probably the mass that's the most common. Okay, so it's like if I averaged 12 and 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 13 and 14, and I averaged those, my answer is going to be pretty close to 12, right? Because there's lots and lots of 12s. And so that's kind of also true for the average atomic mass. So it takes into account how common or abundant each isotope is as well as its mass. So more common isotopes count more towards the average. We call it a weighted average. Okay, so I might consider this. If you find the average age of a teacher, I wrote this last year when I was 31, and her students, age 15 maybe, you don't just average 31 and 15, right? So if I average 31 and 15, I would get 23. Okay, Okay, so when I'm teaching science to you guys, would you say the average age of people in the room when we were actually in the room was 23? No, you wouldn't say the average age of people is about 23. You'd say it's probably closer to 15, right? I might bring up the average a little bit, but not that much. Okay, so we're going to count the 15 more since there are more of them. Like I said, the average atomic mass is closest to the mass of the most common isotope. So here's our equation for this one. And again, feel free to pause and watch this section over a couple times because people tend to struggle with this a little bit. Okay, so we have average atomic mass equals the mass of one isotope times its percent as a decimal. So if 87% of them have that mass, we don't write times 87, we go times 0.87. Right, it's the percent, but as a decimal. We could call that the abundance. And then plus the mass of the next isotope times how common it is as a decimal. Okay, so this says, we don't even have to do the math on this one. It says carbon's average atomic mass is 12.01 atomic mass units. What is the most common isotope of carbon? Well, that number is really, really close to 12, right? So if the average atomic mass is really close to a number, we would say the most common isotope is probably 12. It's pulling the average towards 12. All right, there's some that have a mass of 13 and some that have a mass of 14, and they're pulling the average up a little bit, but the most common isotope is probably 12. All right, this one we have to actually do the math. So a certain element, element X, has 3 isotopes. Okay, so remember the dash is followed by the mass number. So 90% of the element has a mass of 15. 8% of the element has a mass of 16. And 2% of the element has a mass of 17. Okay, so I'm going to take the mass of the first isotope, which is 15, times the percent as a decimal. So I'm not going to put 90. I'm going to put 0.9 plus, right, separate the different elements with a plus sign. Mass of the next one, which is 16, times its percent as a decimal. So 8%, it's not 0.8, it's 0.08. Remember, we have to move the decimal to the left twice to go from a percent to a decimal. And we actually have 3 isotopes, so we need to do one more. 17, the mass of the next one, times the percent as a decimal. 2% would be 0.02. And if you feel really confident on your calculator and you want to type that all in at once, go for it. I'm going to multiply my individual isotopes first. I'm going to go 15 times 0.9, it's 13.5, plus 16 times 0.08 is 1.28, and 17 times 0.02 is 0.34. Okay, so then I can just add those up. 13.5 plus 1.28 plus 0.34 is 15.12, and it's a mass, so our unit would be AMU. Let's go see if this passes the does this make sense test. Okay, so 90% of the element has a mass of 15. Okay, so that's like saying 90% of the people in the room are 15 years old. So if I averaged them all out, the average should be close to 15 because almost all of the element has a mass of 15. Our mass is 15.12. That's pretty close to 15, so it passes the does this make sense test. Let me know if you have any questions. That's the end of the section, folks. Later.